Good morning. This is B. Naresh, working as assistant professor in an ECE department. Today's topic is definitions and terminology, module 4, that is junction, field effect, transistor. So, in this session, we are going to observe some of the important definitions that is related to field effect transistor as well as some current gain and voltage gain parameters. So, the first definition is show the FET is acts as a voltage operated device. So how we can say that the field effect transistor acts as a voltage operated device? Why? Because of that, if you observe, we have the two types of the transistor. One is BJTs and FETs, field effect transistor. So in this case, the BJTs it is called as a current control device, and the FET is called as voltage control device. Why? Because of the drain current is controlled by an applied electric field between gate and a source. So that is the reason the FET here it acts as a voltage control device or voltage operated device. So that is the reason. Whatever the field means, the field in terms of voltage between the two input terminals gate and the source, that is represented as VGS, and it controls the flow of drain current. So means this ID is a functioning of the applied electric field between gate to source, and again the potential difference between a drain and a source, and that is the reason. From this statement, the FET is acts as a voltage control device, or it also acts as a voltage operated device. Now, what is field effect transistor? So here, the drain current of the transistor is controlled by an electric field that extends in the channel due to reverse bias voltage. Why? Because of that. So let us take most of the cases. This is a N channel JFET, and let us consider this is gate, drain, and the source. So if you observe the construction, and based on that construction, then if you want to control let us say this is a internal construction of the JFET. So let us say this is if it is the N channel, this is the N type semiconductor bar, and opposite sides, and we are placing the two heavily doped materials P plus, and one side it is connected with a drain, and on the other end it is connected with the source. Now, based on this transistor FET construction, we know that source is always give the charge carriers to allow the current. Means the charge carriers are diffusing from the source to drain, and the drain current is flowing from drain to source. If you want to control this drain current, now we need to apply a biasing voltage between this gate terminal with respect to your source. Under this condition, when VGS is 0, there is no controlling of the drain current. So means the maximum current is flows from the drain terminal to source terminal. So if you want to control this one, here we need to apply some amount of the biasing that should be in a reverse bias. Means when you are applying the reverse voltage to this junction, what happens? We know that as per the reverse bias concept of the PN junction, so it increases the depletion width, means it occupies some area. That is the reason. So what happens here? The flow rate will be decreases from the source to drain, hence the drain current is controlled. That is the reason. The drain current of the transistor is controlled by the electric field that extends in the channel due to the reverse bias voltage applied to the gate. Hence, this device is given name as field effect transistor. So means this applied voltage affects the flow of conduction. So hence the type of transistor is called as a field effect transistor. Now define the term threshold voltage for FET. So what is the threshold voltage? Actually, what is the need of this threshold voltage? If you observe the normal PN junction diode, let us consider this is the normal PN junction diode. Now we need to identify at which voltage this diode becomes a conducting state. So based on the diode principle, we know that your applied input voltage must be greater than or equal to a cutting voltage. Then the diode becomes, or diode is enters into the conducting state. So that is the reason. We know that this V gamma is either zero point 0.7 or 0.3. So we consider if the silicon material, the current voltage is zero point 0.7. If it is the germanium, the current voltage is zero point 0.3. So similar to that, in a FET construction also, we need to identify at which voltage or at which point the FET is enters into the conducting state, and that voltage here it is called as the threshold voltage. So that is the reason. So the threshold voltage is represented as VTH here of a field effect transistor. It is the value of a gate to source voltage when the conducting the channel begins to connect the source and drain contacts of the transistor to allowing the significant current means. So your applied voltage means you are applying the voltage between gate and source. Whenever this VGS is greater than VT or equal to VT, then only the charge carriers are diffusing from the source to drain to produce the conduction from the drain to source. That's the reason your drain current is increases when your applied voltage is must be greater than of this predefined voltage, that is nothing but a threshold voltage. Now define a body bias voltage. So in this case, so if you are drawing the field effect transistor, we are taking this as a substrate. So that is the reason. A body bias is the voltage at which the body terminals are connected. The body effect occurs when body or substrate. So this is also called the substrate of the transistor is not biased to the same level as of the source. So that is called as a body bias voltage. Now, what are the parameters in threshold voltage? So this threshold voltage generally while defining the field effect transistor. So what are the parameters that affect this threshold voltage? So in this case, the threshold voltage depends upon the gate material as well as the gate insulator material and the insulator thickness and the doping of channel and the voltage between source and the substrate as well as the temperature. So all these parameters defines the threshold voltage while constructing the field effect transistor means. So what type of gate material we are using? Either we are using the P-type material or N-type material. So what type of insulators we are using here? And what is the oxide thickness or insulator thickness between the two conducting plates? And what is the doping concentrations used to form this channel? And how much voltage we are applying between the source as well as the substrate, and what are the temperature parameters also. So all these parameters defines the threshold voltage for the particular field effect transistor. Now, why the FET is known as a unipolar device? So why this FET is a unipolar device means based on the construction of the field effect transistor. So let us take this is a semiconductor material, either N channel or a P channel. One end is doped with a means one end is connected with a drain terminal. One end is connected with a source terminal, and opposite sides they are diffusing the opposite material at the channel. Means if they take another this N channel, it is a diffuser with a heavily doped P plus. If suppose if they are taken the P, then it is a diffuser with N channel. Under this condition, it forms only one PN junction. So ends. So then again, so that is the reason this is called as a unipolar device. So in this, the FET can call the unipolar devices because the charge carrier that carry current through the device at the same time. That is either holes or electron, but not both. And similar to that. And apart from that, suppose if you take in the bipolar junction transistor, the conduction is depends upon majority charge carriers as well as the minority charge carriers. But here in this field case, if you take this material, so this is the connected material is the N type means the source and the drain is connected with the N type, And we know that if it is the n-type, the majority charge carriers are only electrons. And if you take the p-type material, the majority charge carriers are holes, so n. Based on the construction of this field effect transistor, the conduction depends upon only the majority charge carriers, not the minority charge carriers. That is either the holes or electrons. That is the reason. So this device is also called as a unipolar device. Now, show small signal current source model for JFET. If you want to design this small signal current model, first we need to identify the drain current expression. So we know that ID is equal to Gm times of VGS plus 1 by RD times of VDS. By using this mathematical relation, we are going to draw that a small signal current source model. So hence, and let us take this is input side and source is common, and let us take this is the drain. Common terminal is the source, input terminal is the gate, and now we are going to write this expression ID is equal to Gm times of VGS. Hence, and this is the potential difference between gate and the source, and here we are applying the input voltage. Then here this is represented as a Gm, so Gm times of VGS plus another current source is V by R, means that is 1 by RD times of, let's say this is internal drain resistance, and the voltage between this drain and the source is represented as VDS, and this current is represented as the drain current. So this model shows the a small signal model of a JFET in terms of currents. So it's the same I represented here. Now, really, as per this junction field effect transistor, as per the characteristics of the field effect transistor, we have the two types of the characteristics in a field effect transistor. One is a drain characteristics, and another one is a transfer characteristics. Based on these two characteristics, we have some characteristic parameter, that is amplification factor, where mu is amplification factor, and the Gm is the transconductance, and small r is the internal drain resistance, and it is also called as AC drain resistance. So based on that, we have a relation, that is mu is equal to Gm times of RT. So the amplification factor, that is equal to the transconductance is multiplied with the internal drain resistance. Why the input impedance of FET is more than that of a BJT? So for this case, the input impedance of the FET is more than a BJT because the input of the FET is reverse bias. So why? Because of that, just now we observed that if you want to control the drain current, then we need to apply a reverse bias across the gate and the source. So means that for this FET configuration, we taken as gate is made with P-type material, and the source is made up with N-type material. So then we are forming the one PN junction. So for this PN junction, so gate voltage we are applying the, so for the, across the gate we are applying the reverse voltage. So generally we know that as per the principle of the PN junction diode, when a PN diode or a semiconductor diode is accessed a forward bias, it offers very small forward resistance, and when the diode is reverse bias, we know that it offers very large reverse resistance. So generally, how we can define this means, as per the current Ohm's law, I is inversely proportional to resistance. Then we know that if under the forward bias, diode allows the maximum current, means, so when I is the maximum, if I is the maximum means R becomes minimum, And when I is the minimum means that R should be maximum. That is the reason. In according to FET construction, so to control the drain current, the gate voltage should be reverse bias. So if the reverse bias means it offers a very high input impedance, but in the case of a bipolar junction transistor, to satisfy the amplifier principle, the emitter base junction or input junction should be always forward bias. So if the input junction is a forward bias, it offers very small resistance. That is the reason. So always the input impedance is FET is more than that of a bit due to that biasing conditions. So why the NMOS technology means, if you consider the field effect transistor, we have the two types of the field effect transistor. One is JFET, so that is called like the junction field effect transistor, and the second one is MOSFET, metal oxide semiconductor field effect transistor. So in the MOSFET also again we have the two types of the MOSFETs. So means either N type MOSFET or a P type MOSFET. So for this case, why this NMOS technology is a preferred more than PMOS technology. So for this case, the mobility of the carrier, there is a carrier means the charge carriers is the most important deal. So we know that the mobility of the carriers in NMOS is greater than that of the holes in PMOS. So this is only the reason to prefer the NMOS technology or N-type materials, while or we are present the N-channel JFET like that. So the reason is the mobility of the carriers means in a N-type MOSFET or NMOS. So here we are going the N-type material means the majority charge carriers are electrons. So means the mobility of the electrons is very high compared with the mobility of the holes that will be occurred in a PMOS. Hence, we are going to prefer this NMOS technology compared with PMOS technology. Now, what is body effect? So here the body effect to refers the change in the transistor threshold voltage, so that is VT, resulting from the voltage difference between the transistor source and body. So this statement defines the body effect of the field effect transistor. Now define the pinch of voltage means at which voltage the drain current becomes we have the two types of the characteristics. Based on that, we need to define this pinch of voltage. We have the drain characteristics as well as transfer characteristics. So if you observe this drain characteristics, so then we are defining like this. So at this point, this voltage means the drain characteristics is also called as output characteristic, means the output characteristic is drawn between VDS versus ID, and these are the drain characteristics. And if you observe the transfer characteristics, we apply the reverse voltage ends. So this is the VGS, means the characteristics drawn between gate to source voltage and a drain current. When we know that when gate is open, it offers maximum current. So that is represented as IDSS. When VGS is decreased towards zero, or from the zero, then the drain current is decreased. So from this, at which point, if you observe this drain current, at which point the drain current becomes maximum or saturated, that point is called the pinch off. And again, the transfer characteristic, at which point the drain current becomes zero, that is called as a pinch off voltage of a transistor. So that is the reason. It is a voltage at which the channel is a pinched off, means the channel is completely damaged, means there is no movement of the charge carrier. So it completely occupied with immobile ions. So hence all the free charge from the channel to get removed. At pinch of voltage, the drain current becomes constant. So if you observe the drain characteristic, at this point your drain current becomes constant, and that voltage is called as a pinch of voltage of a field effect transistor. Now define IDSS. So just now we observed that. So means at which voltage the drain current becomes maximum, that is called as the saturation. So means that is represented as from the transfer characteristics. When the VGS is 0, and the drain current is approximately equal to ID. Mean drain to source saturation current, that is represented as drain to source saturation current. So that is the maximum possible current with VGS is held at 0. So that is the reason. When VGS 0, it offers a maximum current. That maximum current is called as drain to source saturation current. Now, what is field effect transistor? So a transistor in which the voltage and one terminal creates the field that allows obviously the conduction between the other two terminals, that is in between source and drain means. Otherwise, so the applied electric field to control the drain current, that is called as the field effect transistor. Now, what is ohmic region? So this ohmic region should be observed from the drain characteristics. So suppose I'm going to draw the drain characteristics. Let us take the drain characteristics of the FET, and the drain characteristics drawn between drain to source voltage and the drain current. So generally we know that means when VGS is a constant, or otherwise when VGS is 0, we know that when VDS is increases due to this applied force between source and the drain, then charge carriers concentration rate is also increases, and the drain current is increases. So means it increases linearly, at which point now the drain current becomes maximum, and we know that that point here it is called as a pinch of voltage point. And then to observe this one up to this pinch of region, to observe these characteristics means this is the linear, to satisfy the linear characteristic, the region linear, this region is called as a linear region, means the V is increases, I is also increases. So hence it satisfies the linear properties and linear characteristics, and that region here it is called as a ohmic region. So at this point the FET is acts as a voltage variable resistor. So hence, so when VGS is 0, the depletion resistance is very small, and the JFET is like as a voltage control resistor. So this curve is drawn between when VGS is 0. So at this point, and before this means a pinch of voltage point, the characteristics are shows like a satisfy the linear characteristics properties. So that is the reason. At this region, here it is acts as a ohmic region. So at this ohmic region, here the transistor is acts as a voltage controlled resistor. So or voltage variable resistor, it is also called as a VBR. Now define what is cutoff region. So means what is the cutoff region means? So there is no conduction in the state, or there is no conduction of the low field effect transistor is called as a cutoff region. So that is the reason. This is also known as a pinch off region, where the gate voltage is sufficient to cause JFET is acts as a open circuit as the channel resistance is at maximum. Suppose if you are observe the transfer characteristics, in effect the transfer characteristics are drawn between VGS versus ID, means the gate to source voltage and drain current, means VGS we taken as a negative. So when VGS is 0, the drain current is a maximum, that is represented as a drain to source saturation current. When VGS is decreased from 0, means the drain current is also decreased. At which point now you can observe the drain current becomes 0, and here this region is called as a cutoff region. Okay, what is saturation or active region? Again, so this saturation region or active region can also define from the drain characteristics, means this is VDS and ID. When VGS is a 0, it satisfies the linear characteristics up to the pinch of voltage. The point is the VP, then drain current becomes constant. So this is becomes IDSS, and then we take it as the VGS is 0. So means before this curve, means before this point, this state here it is represented as cutoff region, and this region is called as the ohmic region, and this region here it is called as the saturation region. So that is the reason a JFET becomes a good conductor and is controlled by the gate source voltage while the drain source voltage has little or no effect. Means so with the variation of the drain to source voltage or gate to source voltage, there is no change in the drain current. So means that the drain current becomes constant. That region is called as a saturation region or a active region. Now, what is breakdown region? So here the voltage between the drain and the source, that is VDS, is high enough to causes a JFET resistive channel to break down and pass uncontrolled magnetic current. Means so while drawing this drain current characteristics, then the characteristics taken VDS versus drain current. When VGS is a zero, it offers a maximum current. So hence let us take this is the maximum current at which pinch of voltage, then the drain current becomes maximum. Let us assume even though and this pin is called as the pinch off point, and this region here it is taken as the ohmic region. Then even though if it goes on changing this VDS, what happens here also means so a breakdown will be occur. Means that if a breakdown is occur, there is no controlling of a drain current. So that region is called as a breakdown region. So write the drain current expression in the ID active region. So we know that that is ID is equal to IDSS into 1 minus VGS by VP whole square. Where this IDSS is, we know that IDSS means drain to source saturation current, and the VGS is the potential difference between gate and the source. Potential difference between gate and source, or the applied input voltage between gate and the source, and the VP means the pinch of voltage, and this ID means nothing but your drain current. So hence this is ID relation. Then write the expression for drain source channel resistance. Generally, the resistance means as per Ohm's law, R is defined as the ratio of voltage to the current. Now we are going to identify this drain source channel resistance and under the drain characteristics. So how we observe the drain characteristics? The drain characteristics are drawn between drain current versus drain to source voltage. Hence, so in general, the R is defined as it is the ratio of voltage to the current. So now here I am going to find out the drain to source resistance means. So the drain voltage means, so here the voltage is represented as VDS and the current is represented as means. So how much drain to source voltage is changes with respect to the rate of change of with respect to the drain current. So this is also called as a transconductance. So V by I, that is nothing but a 1 by G. You can also write the reciprocal of the transconductance. So we know that generally the transconductance is nothing but a ID by VGS, ID by VDS. Now define the noise figure. So in most of the cases, this noise figure for the field of a transistor is normally specified in the data sheet as it is also called like the spot noise. So this spot noise at some particular frequency, and here this noise figure will vary with the frequency as well as with the resistance of the input of the device. So what is gate leakage current? So we know that a leakage current means due to the when the temperature is the changes, we know that a reverse saturation current is increases in diodes as well as the transistor. So that current we can also call as leakage current here. So that leakage current is also observed in a reverse bias condition. That is the reason. The reverse bias gate to source current with a drain shorted to the source because the leakage current across the reverse bias PN junction in the case of a JFET and across the capacitor in the case of MOSFET. is a very small and the input resistance should be very high. Why the input resistance is very high means that input junction means the gate to source voltage. Across this gate to source voltage, we apply a reverse bias voltage or a negative voltage means gate is a bias. Gate means a negative voltage is passing through the gate terminal. So what is VGS of any FET? So if you observe this transfer characteristics, so the transfer characteristics are drawn between VGS versus drain current. When VGS is a 0, the drain current is defined as drain to maximum. The maximum current is defined as drain to source saturation current. So means when VGS is a 0, the drain current is approximately equal to drain to source saturation maximum current. When the VGS is decreased from 0, ID is also decreased from drain to source towards 0. So means when VGS is decreased from 0, at this point, this voltage is called as VGS off state. So the value of the VGS that completely pinches the current to 0. So that is the reason. At which point the drain current becomes 0, that magnitude is also represented as VGS off. So generally this VGS off is also called as the pinch of voltage. So define MOSFET capacitors. The oxide layer below the gate terminal is very good. Means while defining the MOSFET capacitors, so means first we need to take the semiconductor and we need to diffuse the source and drain. Then we need to place some insulator. So this is called as an insulator. Then after this insulator, we need to place the metal. So here, metal is a conducting and the semiconductor is also a conducting. In between these two conducting plate, we have the one insulator. So hence it is acts as a capacitance. So that is called as a MOSFET capacitors. So what is CMOS stands for? So here the CMOS stands for complementary metal oxide semiconductor. Then list the operating modes of the MOSFET. So we have the two modes here. One is a depletion mode, another one is enhancement mode of operation. So what is meant by gate source threshold of the FET? So means at this the voltage at which the channel is completely cut off and the drain current becomes a 0 is called as gate source threshold voltage. Also it is also called as VGS off. So this is called VGS off. So what are the operating regions of a JFET? So here we are having the, so already we discussed that one. We have that one ohmic region, pinch off region and breakdown region. So also we have one more region that is also a saturation region also. So define the amplification factor in the JFET. So means that amplification factor in the JFET is represented as mu. So it is a negative. The rate of change of drain voltage means that is VDS. So with the gate to source means generally any gain. So the gain is defined as the ratio of output parameter to the input parameter. For this JFET, the output is defined in the drain to source voltage and the input is measured between gate and the source. Hence, the amplification factor is defined as it is the ratio of drain to source voltage to the gate to source voltage by making the drain current is constant. So hence, the rate of change of drain to source voltage to the rate of change of gate to source voltage while your drain current is constant. So why this input impedance effect is very high in comparison with the BJT? So we know that input junction is in a JFET, the input should be reverse bias. Hence, so whenever the particular PN junction is a reverse bias, it offers very high input impedance. But in the case of bipolar junction transistor, we know that input junction should be forward bias and it offers very small impedance. So why FET preferred as a buffer amplifier? So most of the cases we are going to prefer the FET is a buffer measuring the instruments receivers since they have the high impedance as well as low output impedance. So due to this property, Most of the cases, the FETs are used as a buffer amplifier. Then show the symbol for P channel JFET and N channel JFET. So these are the symbolic representations for N channel and P channel JFETs. And show the symbol for P channel depletion MOSFET as well as N channel depletion MOSFET. So these are the N channel depletion MOSFET and P channel. It contains the three terminals: drain, source, gate, and one extra, the fourth terminal is the body. It is also called as a base. Now show the symbol for P channel enhancement and N channel enhancement. So the difference is due to for depletion and enhancement. In depletion, a channel is established between source and the drain. But in the enhancement mode, there is no channel while constructing the transistor. So hence, these terminals are individual source and the drain. So what are the parameters of JFET? So we have the three parameters. One is drain resistance, that is also called internal resistance. One is transconductance, GM. Another factor is amplification factor, MIN. So means there are three parameters: internal drain resistance, transconductance, and amplification factor. So list some advantages of FET. So these are some advantages. So in effect, the input impedance is very high, and you have some high input resistance. The noise is very less, and it also has some zero offset voltage and a zero drain current. And we can easily fabricate this device complete with a bipolar junction transistor. So up to this point, in this session, we discussed some of the definitions on module 4, that is junction field effect transistor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.